Okay, we are now recording. I have just a couple of minor announcements, and just preaching to the choir here. Two of you have turned in papers in this class. One has not. That must not be right. Wait a minute. Yeah. But no one's turned in the first test yet, right? Right, okay. You're working on it. So I need those first tests in. I need a paper and or a first test from the other student. And we are, let's see, have I given you the second test yet? Oh, I haven't. Okay, that's going to be this chapter. Right, okay. Yeah, that's right, because the end of 12 and 13 was the first test. This will be the second test. Okay. So, one other, I guess, minor announcement is, sort of the good news, bad news situation. The good news is next week is Thanksgiving week. But the bad news is there's no classes at all next week, so we won't meet at all. Next week, isn't it? What's that? I know. Yeah. Say again? Yeah. Like today, I don't have the calendar up here now, but today's the 13th. So next Monday is the 20th, and then the 21st is Tuesday, 22nd is Wednesday, and 23rd is Thursday. Is that right? Yeah. And that is Thanksgiving. So, yeah. Next week, you see what they do in the two-year college system. Have you been here before?
It's a transcript.
Okay, right. Okay. What we do in this, it's a little bizarre. In the two-year college system, they have, we have Thanksgiving, you'd have Thursday, Friday off anyway. And they like to have their ACCA meetings, that's the Alabama Community College Association meetings, for 2 or 3 days, okay? And since we already have the last 2 days off this week, they just scheduled to have the ACCA conference start on Sunday afternoon, and then go Monday and Tuesday, and then the schools are up to them. Well, then you're back on campus for Wednesday, okay? So, since there's a good number of people will be gone for those meetings, they just make those professional development days for us and a big holiday for you. So you have the whole week off here, and we are going to be here, but not necessarily on this campus. We'll be on the Birmingham campus Monday and Tuesday, and then probably back here. I'll be back here on this campus on Wednesday. That's how we usually run it. So there's no classes at all next week. The college is open, so if you need to do business with the college, if you need to see an instructor or an advisor, most of us will be here. Not that many people are going down to Montgomery. That's where the meetings are, just because they're in Montgomery. I don't have the money in my budget to fund, to send a lot of people down there. I think just 2 people from my department are going. I talked all that and I forgot to mark you here. Okay, let me mark you here. So most of us will be around Monday, Tuesday, or Wednesday. But be sure you check with the person before. Don't just assume someone's going to be on campus. Check with them, make sure they're going to be here. But every office will be open. It might be understaffed, but they'll be open. All right, and then there's one other thing. That's about my office hours this coming Friday. Now, I haven't figured out exactly what I'm going to do yet, but what my wife recommended I think is a good idea, so I've got to check with them and see. I need to get my tag transferred from my old vehicle to my new one. I've got the tag, but I have to go down to DMV, Department of Motor Vehicles, to get it done, and that's in the courthouse. I don't know what the hours are, And I don't know what time they open on Fridays. I'm hoping they'll be open by 8. It may be before 8.
I think the one in this is
8 to 5 on Fridays? Okay. I'm hoping that's going to be true for downtown too, because I can be at the downtown post office, courthouse before 8, so I can be close to first in line. But I'm afraid that if I wait till later in the day, there'll be a long line. So I'm going to try to get down there before 8 o'clock and try to be as early as possible. So I'll be coming to campus later on Friday, but I'll stay later. I just don't know what time that'll be. I'll be there 4 hours, but hopefully somewhere between, I'm just going to say 10 to 2. But I've got to work that out. So anyway, that's the only other announcement I know about. Okay, next. Any questions on anything we've done so far? All right. We're in section 4.5, and this is talking about a new term, and this is called a gradient. And this term, the gradient, is basically, this is a gross generalization, but it's how I think of it. A gradient is to a surface like a tangent is to a curve. Okay? If you have a tangent line, if you have a curve, and a point on the curve, the tangent line is the direction that the curve is going at that point, and it only touches at that point and is there. Now, a gradient of a function f of x, y, and it actually would be for f of x, y, z if you had three variables at some point a, b, or a, b, c if you had 3 variables, would then be a vector, just like a tangent is actually a vector pointing in a direction. And this vector has an unusual symbol. It's this symbol sometimes called the del. It's an upside down delta. And what that means is gradient. Now, because it is a vector and it doesn't obviously a vector, usually when I write it, I put an arrow over it to indicate to you, this is a vector. Okay. So del f sub p, and that means, okay, now let me start over a little bit. This function is a scalar function. It's just some function of x and y. You get an x and a y, and here's a z, that's a function of x and y. Any two x, y, they'll produce some other z. Okay, so that's the scalar. At some point, a, b, okay, a on the x, b on the y, some point a, b, that has a value up here. Okay? The function has a value. So the gradient of that function at that point AB, x and y is AB, is the vector del f of p. The gradient of that scalar function, the vector gradient of that scalar function at that point p. Okay, that's what those symbols represent. And here's how we define it. If you're on 2 space plotting onto the 3rd space, 3rd dimension, then it's the vector that is the angle bracket, vector symbol, the partial of f with respect to x evaluated at AB, comma the partial of y with respect to x at AB. So in other words, it's the slope of the tangent line in the x direction, okay, is your x component, and your slope of the tangent line in the y direction is your y component. Somewhat speaking. They're not exactly tangent lines, but they are if you held the other variable constant. 3 variables at some point p, a, b, c, then the gradient of f at that point p would be the partial of f with respect to x at that point a, b, c, comma the partial of f with respect to y at that point a, b, c, comma the partial with respect to z at that point. That's what a gradient function is. Take the partial derivatives for each of the corresponding independent variables, evaluate them at that point, and those are the components of the vector at that point. Okay? Now, here is a figure, and this is a figure for, let's back off and just put one more thing in here. Just to remind you, I think would probably be the best way to say what this represents. Another way to write this, the gradient of some scalar function f at some point p, well, let's just leave the p off, at any point p, okay, at any point, okay, at any point will be, and written a different way, they use the sub-notations here. You could just say partial of f with respect to x, comma, partial of f with respect to y. Okay. That's what that's saying. Not even at a particular point. In general, that's the formula for the gradient. And in 3 dimensions, the gradient of f would be the partial of f with respect to x, comma, partial of f with respect to y, comma, partial of f with respect to z. Okay? And technically, even though gradient is sort of has a physical meaning, if you had in space, you could keep going like that. But unfortunately, we don't live in space. Okay. So, example 1 is drawing gradient vectors. Okay. So I'll go on and put the slide up, but give you what the problem is. It says let f of x, and it's written down here, f of x is equal to x squared plus y squared. Calculate the gradient del f and draw several gradient vectors and compute the gradient vector at point P where P is 1, 1. So let's start with this. The gradient, that's a pretty ugly del. The gradient of f is what? It is a vector. That's why I put the arrow over it. Okay. Don't know if you can see it well enough. Let me blow it up again for you. Okay. Here's the function. Alpha of xy is equal to x squared plus y squared. What's the gradient of alpha? Well, I started right here. What would that be? It is a vector sum. Is it partial? Okay, it's the partial of alpha with respect to x. Yes. 2x is the x component of the vector. No, okay. All right. Sort of get an idea of what you're doing. The partial of this with respect to x is just 2x. Okay? You don't put the y squared in there because that's treated as a constant, and the derivative of a constant is 0. And then the second component of the vector, the y component of the vector, is the partial of this with respect to y. And there the x is a 0, as constant, so that would be what? 2y. All right. So there's the partial of f with respect to x anywhere. I mean, the gradient of f anywhere. Okay. Sorry. It says draw several gradient vectors. Okay. And what I'm going to do, rather than drawing them, I will zoom in on them. Okay. And keeping that vector symbology down there, here would be it. Pick a point, any point. 1, 1, okay? At 1, 1, you go 1 here and 1 up there. There's that. And then you plug in 2 times 1 is 2, and 2 times 1 is 2. So that would be a vector in the 2, 2 direction. So there would be the gradient vector 2, 2 at that point. So this is the direction that would be heading there. Any other point? 0, 1. Okay? 0 on x, 1 on y. That would be 0, 2. So that would be pointing straight up here. Okay? Magnitude of 2. Take a little point, negative 1/2, negative 1/2. Here's the negative 1/2 here, negative 1/2 there. There's the point. Plug it in, that would be 1, 1 in that direction. The point is in parentheses, the vector is in angle brackets. So the gradient of f at the point, negative 2, 2, will be negative 1, 1. Okay? The gradient at 1, negative 2, here's 1, and negative 1/2. Here's 1, negative 1/2, there's your point. The gradient here would be 2, negative 1. So 2 in the x direction, negative 1 in the y direction. So that would be several points. The vectors are not drawn to scale, it says, and truly they're not. Obvious, not to this scale anyway. Relative to the other vectors, they are approximately right. This would be the longest of the 2, the shortest of the 2. Longest of the 3, shortest of the 3, the middle of the 3. But not necessarily scale. Okay? And then the third part that you already said, draw several gradient vectors, then compute del f at the point 1, 1. We've already said what it was at 1, 1. That gradient vector is 2, 2. 1 for x down there would give you 2 times 1 is 2. 1 for y would give you 2 times 1 is 2. So that would be the vector 2, 2. Okay. Now, example 2 I don't think has a graph or a place for it. So let's just remove all the ink from the slides. I guess I have to reduce it first. Okay. Let's do example 2. Gradient in 3 variables. Calculate del f, and the book doesn't do this. Now, I can't tell what the book's doing here. In most books, when they do that del, they make it fairly bold looking. This book, I can't tell if it's bold or not. It doesn't look bold to me. That's why I put the arrow over it to remind you. It is a vector. Gradients are vectors. Calculate del f at the point 3, negative 2, 4. At 3, negative 2, 4. Okay? Where your f of x, y, z, three-dimensional vector here, is equal to z e to the 2x plus 3y. Okay. So let's first do our del f at any x, y, z. And what would that be? Give it to me generically first if you want to. That probably would be a good idea. What is the definition of del f? F with respect to x, comma, partial of f with respect to y, comma, partial of f with respect to z. So now we have to figure out what each one of those is. So let's first do f sub x, since that's the one we need first. What is f sub x? That's a z in front. variable z. What's that? I can't quite hear.
Is it z times e to the 2 plus 3y?
Okay. That is the first part of it. Okay, what were you doing there?
You said with, so the first one is with respect to x, right?
Yeah, with respect to x. You started off just right. This treat as a constant because you're taking it with respect to x. So if that were a constant, the constant would be there. So you're absolutely right. It would be a z, and then the derivative of an exponential function is itself, e to the 2x plus 3y. But then you have the times 2. Okay, that's the rest of it. So your del f will be the vector. The first component is 2z e to the 2x plus 3y, comma. Okay. Now what? Partial with respect to y would be 3 z e to the 2x plus 3y. So that comma, after the comma, would be 3 z e to the 2x plus 3y, comma. That's wait, not the z. Okay. When you're taking this partial with respect to z, let me write it down. F sub z. Okay. You count the x's and y's as if they were a constant, right? And e to a constant is a constant. So it would be basically the derivative of cz. If e to that thing is a constant, then just move the constant in front. Z is your only variable, and it's some constant times the variable. And what's the derivative of a constant times the variable? Just the constant. So that would be, forget the z here. When you take a derivative, it goes away because it's to the first power. Now, if that was z squared, it would be, 2z, But this isn't. It would be e to the 2x plus 3y. So that's your last, in fact, I'll erase this and just have a big blank there and close it out. Okay, so that's your partial, that's your gradient of L everywhere. Okay, but it didn't ask for it everywhere. It asked for it at the point 3, negative 2, 4. But guess what? You do this first. You don't plug in first, then take a gradient. No, that won't work. You take the gradient at x, y, z, and then you plug in. So then what they're asking for is del f at 3, negative 2, 4. Oops. Put a angle bracket there. That's a point, so that is a parentheses there. And this will be a vector. And the first component is what? Which is your z, you're evaluating at 8. E to the 6. Second, e to the 0, which is 1, so it's just 8. Okay, comma,
12 to the e.
just 12 again, comma, third one's way over there, 1. Okay, there's the gradient at that point. And the x direction is going up by a factor of 8, and the y direction is going up by a factor of 12, and the z direction, and I'm in 4 space now, so I can't draw my hands too well, it's only going up by a factor of 1. Okay? So that would be 8, 12, 1. Very good. All right. Now, here's theorem 1 that puts together a lot of the properties of your gradient. Okay. If f of x, y, z and g of x, y, z are both differentiable functions and c is some constant, then the gradient of a sum of two functions, two differentiable functions, is the sum of the gradients of those two differentiable functions. So you can take the gradient across a parentheses, across the parentheses, kind of like you're distributing it across to the two functions. Okay? And of course, the sum of two functions is a scalar. Sum of two scalar functions is a scalar function. Take the gradient of a scalar function, you got a vector. So this is a vector plus another vector is a vector. Now, for the c is any old constant, the gradient of some constant times a function, because the gradient only deals with the x, y's, and z's, you can take the constant on the outside, and that would be c times the gradient of f. Okay? Just like we've done with functions, derivatives, all sorts of things. All right, number 3, product rule for gradients. If you've got a product of two scalar functions, f and g, then hopefully it would be about like you would expect, because the gradient is acting a lot like a first derivative. Only it's the first derivative of this is a three-dimensional vector, a three-dimensional function, okay? Three-component function, okay? That would be f times the gradient of g plus g times the gradient of f. And the order doesn't matter here because the addition can go either way, okay? And then finally, the chain rule for gradients. If capital F of t is a differentiable function of one variable t, but that t is a parameterized equation of f of x, y, and z, then the gradient of f with respect to that function t is, now this is a scalar function of some individual variable, a single variable, that would be the derivative of f at that variable times the gradient of f at all those variables. So you see the gradient of a scalar function, of a single variable, but that single variable is itself a function of another 3 variables, then the derivative of that first single value function, okay, f prime of t, where t is f of x, y, z, times the gradient of that. So there's where the vector comes in here of the innermost function, but you knew it had to be a vector of those variables also. So it was going to be a vector. Okay, so that's the chain rule for gradients. Now, this is something I haven't figured out about how they do things here. In the summertime, when it's warm, and students wear probably the lightest clothing, I know I do, okay, then they have the air conditioning set way low, so everybody freezes, okay? And then in the wintertime, when it's cool outside, and they finally turn the heat on, they set the thermostat high so that when you have the most clothes on, then it's the hottest. Now, you look like you might be comfortable in here today because they've got the heat on and it's warm. But it's set up to 70 through 73, something like that. And and that's such an energy waste to, when you're hot outside, to cool it cooler than you would keep it inside when it's cold. And heat it warmer than you would keep it in the summer when it's warm. And so they're wasting energy both ways. They're wasting energy to overcool it in the summertime and, well, possibly overheat it in the wintertime. You know, it would be better if they just fixed some temperature and kept it there year round would be better. Or best would be in the summertime actually bump up the thing when you have the least, you know, lightest weight clothes, have it warmer in here. And then in the wintertime, when you're most heavily dressed, that's the time to have it cooler, not in the, you know, not warmer in the winter and cooler in the summer. It just drives me nuts sometimes. Right now, it's so dry. I mean, so warm. Part of it is we got, you know, sun coming in over here too, but all morning it's been about a degree above what it is. Now it says it is at 72. But what I feel coming in here is a lot warmer than that. Okay? And again, I'm sitting right under the vent, so frankly, it tends to dry my head out. So I'm never satisfied, am I? Okay. All right. Let's do example 3. And this is a don't think we have a lot of room to write on that one. We've already written on that one. Let's see. Yeah, we have a little more room to write. We'll write on this one. Find the gradient of, now this figure has nothing to do with the problem. Find the gradient of g of x, y, z, which is x squared plus y squared plus z squared to the 8th power. All right? Now, this isn't written in the same form of what the rule was, but actually, to me, this is the easier way to do it. Okay? What would be the gradient of that function? Okay? Find the gradient of that. So we're looking for del f of this, where it's, so that would be del of the big thing here, the whole function there. How would you do that? Okay, where? Over here? Over here. That's the gradient of g of x, y, z. Okay. Now I put the parentheses in there, and they could be confusing, so let me, because they could be, let me take them out for a momento. Okay. And put brackets in instead, so you can tell the difference between the, okay. Delta g of that, the gradient of that, I'm sorry, that was ridiculous. The gradient of this function g, which is the gradient of the overall thing there. Okay? Say that one more time.
The partial of L with respect to x.
Okay. All right. I'll do what you say. And what is the partial of? And what is your f? That's the thing I'm See, in the book, they have a capital F and a little f, and that, to me, makes it even more confusing. Let me suggest to you what I would do, okay? I like to do the outer function first, okay? That would be 8 times x squared plus y squared plus z squared to the 7th power, right? Okay. Then I do the partial of what's on the inside. And that would be, and since it is a partial, sorry, basically that's going to be a gradient, okay? And a gradient is a vector. And what is the gradient of the inner function there? Two y, right? 2z. Oops. And then dz. I mean, you could say that, but that's it. Okay, that really is all you have to do with it. Now, one thing you could also do, I hate to suggest this because the book hasn't mentioned it yet, you could factor out, and well, they actually have way earlier, factor out the 2 and divide it with the 8 and 16. So this sort of acts like the coefficient part, and that's the vector part. That's why you see. Now let's see how they actually did do it. They did do it that way. They do 16 times x squared plus y squared plus z squared to the 7th power times the vector x, y, z. Okay. While I'm there, let me erase this. Put that in parentheses rather than angle bracket earlier. So that's your chain rule of a function. Gradient of the overall function there is the 8 times this thing to the 7th power times the gradient of the innermost function, 2x, 2y, 2z, vector quantity. Factor out the 2 out of that, put the 16 out here of this thing to the 7th power times the vector, x, y, z. Now, I don't think they said on this one to do it at any particular point. They just said, find it. All right. Sorry, I've got terrible hiccups for some reason. I don't know if I ate lunch too rapidly, which I did, because I had that question. Now, I had less than an hour to eat anyway, and I had that question, and I was trying to rush through lunch so I could finish before I got up here, and it was even late then. And I did drink plenty, but it was after I finished eating. I probably drank too fast, too. So I don't know. Now let's look at the chain rule for paths. Goodness, I'm hot. In our first application of the gradient, is the chain rule for paths. Chapter 13, we represented a path in R3 by vector-valued function R of t, which is some x of t, y of t, z of t. Okay? If you remember back when we were doing that, chapter 13, we had some vector-valued function R of t, and this R of t was the vector x of t, y of t, say t. What? Goodness gracious, I'm saying t and writing all sorts of other letters down. This is nuts. I want to blame it on the heat, but I'm not sure I can. Goodness gracious. x of t, y of t, z of t. Other thing is my mind's going faster than my pen is going. All right. So there's a vector value function, and that is a path, some path that's described in 3 space. When there is no harm in doing so, we think of R of t as the path of the endpoint of vectors rather than just the path of vectors themselves. Okay? That is a kind of a strange statement there. When there is no harm in doing so, of thinking of something, I don't know what harm would be. We will sometimes think of R of t as the path of endpoints of vectors rather than being the path of a particular vector. Goodness gracious. Sorry. I feel like I'm getting heartburn. Rather than as a path of vectors themselves. You know, here is the figure they're referring to, and it's kind of a bizarre statement. Okay. Now, it looks like what we're drawing here is the path of the vectors themselves. Okay. Here's a vector who moves along this curve and does like this. You know, that's what it looks like there. But they're saying think of it as a path of the endpoint of the vector rather than the path. Well, the endpoint of the vector would be the one that's down there at the origin, pointing outward, and its endpoint is then going like this. So that would be the path of the endpoint, but they drew it as if it's the path of the vector, c. Okay? So, and they say this c of t is x, y, and z, x of t, y of t, z of t. Well, now notice here, now this is the part that I find especially strange. When they're talking about a curve, a path, okay, notice they bold the c as if it's a vector, but they put parentheses around it as if it's a point, okay? And to me, that notation is so incredibly sending cross messages. I mean, it's just, why don't you go on and call it a vector, you know? Because when you take a derivative, it's going to be a tangent vector, but they are saying this itself is just a point with those coordinates, x, t, y, t, z, of c, okay? Why not go on and call that a vector? I don't know. So the tangent vector, c, and now this is bold and that's bold, but this is not written as a vector, but that is. The tangent vector c prime of t, bolded, okay, to a path c of t, bolded, but then they put it in parentheses as if it's a point, a series of points, okay? But why then bold the c? If it's a series of points, keep it just a regular c, not bolded. But they don't. They sort of mix it up. Okay. But never mind. I mean, don't let that get you messed up here. Okay. Now, I'm sorry. Take some of this back. That's how they said it in the previous edition. This is the first time I've taught it in this new edition. I just happened to glance at that. They changed this, okay? And they changed this to be an R of t, so I'm going to shrink it. Oops, I didn't. Okay, wait. Okay, why have I not got my pen? Okay. It was shrunk, okay. So, this now they're calling R of t and making it a vector, and then below here, they do have angle brackets. So evidently enough, other people griped about this, and they have changed it. Sorry, I got off onto it because that was what was on the slide. But in your new edition, they put the angle bracket in there. Thank you very much, okay? They're not even bringing up the C anymore. That was so confusing, okay? Now, that tangent vector r prime of t is then merely, if this is xy of t, then r prime of t is going to be a vector x prime of t, y prime of t, because all these are differentiable functions, z prime of t. Okay. This is better than they did it last time. Sorry about that. I started teaching it like they did before, but I just realized they're not doing that anymore. Okay, so thank you. They corrected it. Now, the chain rule for paths. Now, they're going to do something else a little strange here. This is their... This is stuff they're not saying anymore. What we just said about R of t was correct, and those are angle. No, they're not. Okay. Let's back up again. Sorry. Before they introduced the C and had it bolded and stuff, now they're leaving it R, but here's what they say. You don't have your book in front of you. Let me read it to you. When there is no harm in doing so, we will sometimes think of R of t, and they bold that, as a path of the endpoints of vectors rather than a path of the vectors themselves. And they show this figure, but with R's in there. Okay? Thus, we might write R of t as, and this is when they go back and do the same crazy thing they did before. They change this from a vector notation, which they used in 14 and chapter 13, to an angle, to a point notation that they're using here. We might write R of t as that, rather than R of t as with angle brackets on it. By definition, R prime of t is a vector of the derivatives as before. So, and that's where they get the next slide, which was this one, except I can't write on it. They're changing this back to an R. They bold it, which means it's a vector, but they still keep parentheses there and make R prime of t, even though it's based on the other one, that now is an angle bracket. Now, let me blow this up and see if you can see that angle bracketness of it. Okay. This is clearly a parentheses here, here, and here. So they took the R of t, they still write it bolded, they still have it as if that's a vector, except they put parentheses here. The R prime of t, which is based on that, is given as a vector quantity, x prime of t, y prime of t, z prime of t. So I still haven't figured out why they changed this. And all comes from is the path of the endpoint rather than being the vector itself. And that's what, because it's a path rather than a vector, they put it as parentheses. And I don't know why. I mean, it would work just as well, it seems like to me, if you kept it in vector notation, but they don't. The chain rule for paths deals with a composite function of the type f of r of t. Okay? So let me shrink this back. The f of r of t. Okay? Now, is that r of t the vector r of t or the point r of t? They're not real clear. Okay? Says, recall from section 13.2.2 that r prime of t is the tangent or the velocity vector that is tangent to the path and points in the direction of motion. Okay? If it's a one-dimensional path, then that's fine. Yeah, that's perfectly what we're used to. Okay? We use a similar notation for paths in R2. The chain rule for paths deals with the composite functions of the type f of r of t what is the idea behind the composite function of this type? As an example, suppose that T of xy is a temperature at some location xy. Now imagine a biker, we'll call her Alexa, rides along a path r of t, and that's what this figure is basically showing us. Goodness gracious. Okay. Now, in the new text, it's Alexa, and in the last edition, it was Chloe. I mean, it's nonsensical name. I mean, they're fine names, but they're just making up a name. So why change the names? I don't know. It's whatever. So anyway, here, Alexa or Chloe, riding along a path r of t. Now that's a path, and they're calling it c of t. Now the book is calling it r of t. Of course, when I go to write on it, it's going to shrink. Okay. And this is such small, but if I leave it out there, I can't draw on the board. So I'm going to try to figure it in somewhere. Make this r of t, this r prime of t, that is a vector. Okay. Now I think that looks more like the one we have here. And that's the gradient vector of your temperature as a function of x and y. So here's the rest of the story here. Imagine a biker, we'll call her Alexa, riding along that path r of t, which the book was, the slide was showing as the c of t, but now they've changed it back to r of t. And this is the path the rider is taking. Suppose that Alexa carries the thermometer with her and checks it as she rides. Okay. Her location at time t is r of t, so that her temperature reading at time t is a composite expression okay, I've lost the place here. Okay. Okay. What is the idea behind the composite function of this type? An example, suppose that T of xy is the temperature at location xy. Okay? So here she is at xy here. It matters any, but that would put her, it looks like, fairly close to Yellowstone maybe. Okay? Somewhere in that general area. Okay? Now, let's see if blowing it back up will help any. It will make my writing look even worse, if that's possible. Okay. So here's her position here at R of t. They draw that as a vector, but we're using it as a path, of course. Oh, here she is, sorry. So that's not, that puts her in South Dakota, I don't know, somewhere there. Okay. So here she is at R of t, and her top following along this curve on R of t, okay, x of t, y of t, okay. Now, this is their velocity function. The displacement function would be, if you imagine the vector r going like this, is the path that the endpoint is taking. So that's your r of t. And at any point along here, she has a unique temperature, okay, depending on the time of day and everything else. So this is some t of x, y, and z, because that depends on where she is. Warmer down there than it is up here. Cooler up here than it is down here. You know, drier here than it is over. I mean, whatever. But the temperature is a function of where she is, x and y. Okay, or her components of your displacement vector. Okay. Now, that temperature, since this is a scalar quantity, a scalar function, t of x, y, you can take a gradient of that, and that tells you how the temperature is changing with time. Probably as you're going northward, the temperature is dropping. As you're going eastward, it could be rising or dropping or staying somewhat the same. So Chloe's temperature changes at a rate. This is the change of the temperature times her change of speed here. That gives you a change of the temperature's change, the rate of the temperature change. And that is a composite function. Okay? Riding along a path, this is Alexa now, we suppose she carries a thermometer with her and checks her temperature as she rides. Her location at time t is r of t, so her temperature is reading at time t for the first is the composite function t of r of t, that's Alexa's temperature at some time t. The idea that okay. All right. So since the writing on here is not corresponding to the writing here very well. Oh, let me also change these. I changed the R is there. This will also maybe improve. I don't know if it will or not. That's so small I can't see. That's an R there, and this is a R prime here. Okay. And it's also a vector. Okay. And R is given a vector notation, but it's treated like a scalar function of time. And you dot that, the del t evaluated R of t, okay, times the R prime of t. That's it. How her temperature is changing, Alexa's or Chloe's or whoever. This is the rate at which the temperature is changing with position. The rate at which position is changing with time, that's the R prime of t. And the dot product of those is then the rate at which the temperature is changing with time. Okay. And I think that's what they're trying to say here. So, let me write this one more thing in here. So d by dt of t of r of t, okay, that would lead to the chain rule for paths, okay? And it's telling us that is that dot product, okay? All right. To me, all that lead up was almost more confusing than it's worth, okay? Because I thought they did a really poor job, and I probably did even a worse job because I was trying to figure out what they were trying to do. But here's the chain rule for paths. If f is a scalar function, and again, they've made this an r, so I'm going to have to shrink it back and make that a r of t, and the r of t, both the f scalar function and the apparently a vector function, okay, are both differential. Then if you're taking the derivative with respect to the variable here, the independent variable t, of this composite of f of r of t, there's your r of t again, and make this r prime of t, okay, f of r of t, okay, that's equal to the gradient of f at r of t. Goodness gracious. And the writing is so stinking small, I can hardly do anything with it. Okay, those were C's and now R's, all of them. So the rate of change of this function as the scalar function of that positional vector or pathway, okay, the rate of change of this is the change of F, which is the gradient of F, dotted with the change, you're basically almost do a chain rule, d by dt of r prime of t. So it's just about what we had before, kind of written in a different order. Explicitly in the case of two variables, if this r of t, again, that's an r, is equal to xy, okay, two variables, x of t, y of t. So that could be 2 or 3. Then d by dt of alpha of r of t. It's so small on my screen, I can't read it. So I'm hoping I've got it all. Then the time rate of change of that function, scalar function of this apparently vector function, okay, would be the gradient of the outer function, partial of alpha with respect to x, partial of alpha with respect to y. And if this happens to be three-dimensional, then you have this third one there. Dotted that with x prime of t, y prime of t, okay? Those are vectors too. And then this would be partial of alpha with respect to x dx dt plus, comma, plus, because it's a dot product, partial of alpha with respect to y dy dt. Okay. Now, this actually looks like it makes more sense than what the rest of it did. You're taking the derivative of a function of 2 or 3 variables here, okay? That's a vector function. Then it's partial of alpha with respect to the first times d at x dt, plus partial of alpha with respect to the second times dy dt. And that, hopefully, is what you would have guessed that would be. And that really is expressing the chain rule for paths. Okay? So, all their explanation, I don't know. Maybe it made sense to you. It made a little less than real sense to me. Need to take a break? Okay, I think I'll pause too because I need something to drink. I hit the wrong key. All right, we just finished with chain rule for paths, which your text also has in three-dimensional. This would be this. I wondered why they didn't have this before. If your R of t was equal to x, y, z. Now this is, okay, they're doing it to me again. Here in the theorem, now they put the R back as a vector. I don't know why they ever changed it, but they are putting it back as a vector. Good for them, because it should have been a vector all along. X of t, y of t, sorry about that, z of t. And their notation, you have to really stare at it, or I do, to figure out whether it's an angle or a parenthesis. That is an angle. Then, the same thing we just did, derivative with respect to t of this f of r of t, okay? Was it because you're getting too hot, or? Yeah, I know I'm not feeling well either. I don't know. I thought maybe it was something I ate for lunch, but I don't know if it's not. What's that? That may be why. Yeah. Okay. But I appreciated the break because I needed to get something to dampen my eyes and also to cool me off a little bit. So I drank a drink out of the fridge and also ran water over my face. Okay, I was just saying this now. When they, right after the theorem, where this one talks about case of two variables, your book says a case of three. So I went on to write down the thing, and the first thing they said, explicitly in the case of three variables, if R of t, just like they did there, is equal to, and then what did they do? They put an angle bracket there for x of t, y of t, z of t. And whereas before they had changed it from angle to, intentionally changed it from angle to parentheses, they went back to angle. Thank you. I mean, that makes so much more sense with it being an angle bracket. Then, this thing here, where R is that function, is simply the partial of f with respect to x, comma, the partial of f with respect to y. That's the gradient, right? Comma, partial of f with respect to z. Okay? Dotted with, and this is exactly what they're saying here, it's the gradient of f with respect to r, dotted with the tangent vector, the first derivative of your displacement vector, which would be angle x prime of t, y prime of t, z prime of t. Okay, and that's an angle vector. Okay, and then they write out what that is, just as before, and that is your dot product, so you lose the vector characteristic, partial of f with respect to x times dx dt, and that is a derivative because that's single variable case, plus the second entries, partial of f with respect to y dy dt, plus the partial of alpha with respect to z dz dt. Okay. So they got all that, whereas they said for 2 dimensions, this your book says for 3. It's good to list them both. Better list the 3 and then say, or you can just leave off the z's for the 2-dimensional case. Now, they have a little proof here that goes on kind of forever, and it's worth a read to follow it, but I don't want to take class time to, it would take almost the rest of the class to go through all that. Let's go on to the next example, okay? And this is it. Let me first blow this up. Okay. The temperature at location xy is T of xy is equal to this. Oh, they don't give it here. I thought that was somewhere on here. It's not. Yeah, it means they're going to have to shrink it again and write it on here. The temperature at any position xy is given as T. And usually, by the way, have you had physics? You taking it now? Okay. Capital T is temperature, small t is time. Okay, you probably have hit that before, just in case. Okay, so the temperature at any position xy, now this is on a 2-dimensional type situation here, is given as 20 plus 10 e to the minus 0.3 times x squared plus y squared. And then they have degrees Celsius. Now, when I first looked at that, I thought they were doing a composite function because, just like mine, the degree is up there right next to the exponential thing. That's not, that's degrees Celsius. Those should be together, okay? But that's the temperature at any position. A bug carries a little tiny thermometer along that path, and here's the path the bug is following, and that, I think, is this one here. This will be R of T is equal to, and look here, they did an angle bracket again. Good for them. Whereas I can't read this until I get really close. They have parentheses here. Make them angle brackets. Thank you very much. That was just about the weirdest thing in the previous edition. And the weird thing in this edition, they almost went back to doing it, and now they backed away and not doing it anymore, but it's confusing. So there's R of T is cosine of T minus 2, comma, sine 2T. Okay, where T is in seconds. And here is the figure of it here. Okay. There's the path he's doing. How fast is the temperature changing at T is equal to, little t, time is equal to 0.6 seconds. Okay. Now, what you have to do here is start with, where are you, Waldo? Okay. At T is equal to 0.6 seconds. Okay. You got to first figure out where you are. Okay. So your position at 0.6 seconds is equal to, here, cosine of 0.6 minus 2, comma, sine of 1.2, because it's 2t. Okay? When t is equal to 0.6 seconds, this is cosine of t minus 2, sine of 2t. Okay? So let's carry that on out. Goodness, this is tiny. So there's where you are at 0. Why am I writing it back down there? Let me write it where I was writing it. So much, little more room to work. Okay, so this R of 0.6 seconds is this angle. Cosine of negative 1.4, comma, sine of 2 times 0.6 is 1.2. Okay, now, remember you're dealing in radians here, not degrees, okay? Degrees in Celsius, not degrees in angles, okay? Now you have to think for yourself here, where are you at negative 1.4 basically seconds, okay? Well, cosine of a negative number is the same as the cosine of the positive number, because cosine is an even function. Okay, 1.4, this is a bit bizarre. So think in terms of trig here. Okay? 1 radian is about 60 degrees. It's 57.8 or something like that. That's 1 radian. It's up here, remember? Now 1.4 of that is 1. 1.4 is a little less than half. That puts it over here in the second quadrant. Okay? So I'm not buying this, okay? The x component of this, oh wait, yeah. But the x component is cosine of that, and cosine of that would be a negative quantity. And they show it being positive here. If you got a calculator, do that. Do cosine of negative 1.4. Don't you get a negative value? Yeah, be sure you're in radian mode. Oh, really? Huh. Wow. What's the cosine of 1? Negative 1. Negative 1. Yeah. Okay, yeah, that's right. Is it 0.5 on the nose? Or 0.5 was a few decimals. Okay. I'll buy that. It's something short of, see, 60 degrees, cosine of 60 degrees would be 0.5. Okay? Or negative 60 would be negative 0.5. Oh no, 0.5 also. Okay? Okay. This would be pi is 3.14. So pi halves is 1. Yeah, that's right. I'm sorry. Yeah. You're still in the first quadrant. Okay, I'll buy that. Okay. For some reason I was thinking it was further out than that. Okay. Because here's, yeah, pi is 3.1416. So pi halves is 1.5, yeah, 1.5 something, another 57 0.08 or something like that. So 1.4 is just before you get pi half. So yeah, you're still in the fourth quadrant. It's still positive. So yeah, that looks reasonable. Okay, sorry about that. I was skeptical. Okay. Okay. But it's the number. Okay, say again what you said it was. Cosine of negative 1.4. It should be less than 0.5, shouldn't it? Oh, you said once. Oh, 0.169. Okay. I thought you said 0.69. Okay, that's fine. Okay, so the x is 1.169. So just barely on x, and then your y value is sine of 1.2. 1.2, if this is 1.2 is still in the first quadrant, okay? But it's going to be a bigger number because you're getting closer to 1. So sine of 1.2 is yeah, okay, that makes sense. Good. 0.9. That looks good. This is 0.1. Okay, so that's where you are. Okay, got that right finally. Okay, so let me erase this down here. Goodness gracious. Over no need to room, I'm afraid. Okay. Okay. So that's your position. That's where you are. And that would be, I'm going to put it down approximately 0.16 or something like that, and this would be 0.9 or something like that, just to give us an idea, to help me remember that, okay? Now, that's where we are, okay? Now, remembering, this is our x of t, that's our y of t. We don't have it as t, but it's here. There's the x of t, there's the y of t. Okay. Now, your temperature at any xy there, including these here, is going to be 20 plus 10 times e to the minus 3 times the x squared. That would be about 0.16 squared, which I'm thinking is get into that. And the y squared would be about 0.81. Okay, so you're going to add those two together and multiply that, and that's going to give you your temperature at that position. Now, you don't have to do that. Temperature, okay, just in a second. How fast is the temperature changing at time t equal 0.6 seconds? Okay, so how fast is it changing? In other words, dt, only the top t's temperature, the bottom t's time. Okay, and this would be the gradient of this thing, the gradient of t, okay, times dot product with r prime. Okay, so the next thing we have to do, if this is r of t, then r prime of t is equal to, what's the derivative of cosine t minus 2? Yeah. Negative sine of t minus 2. Okay, and you don't have any chain rule there because the t is just that. I don't have room to write it. What's the derivative of sine of 2t? You got it. You're really not feeling well, are you? I can tell. I'm sorry about that. I'm feeling better now that I got something to drink, but sorry you're feeling worse. Okay. So basically, we do the dot product here. The gradient of your tangent of your temperature function would be the partial of this with respect to x. Okay? So let's do this. Gradient of t, and this will be a vector, the partial of t with respect to x, comma, the partial of t, capital T, with respect to y. And what is the partial of this with respect to x? Well, the 20 contributes nothing here. Okay? And you've got 10 e to the minus 0.3 times x squared plus y squared. Okay? Right? And then times the derivative of your argument here, which is with respect to x, would be negative 0.03 times x squared. That would be negative 0.06 x. So multiply that by our 10, and that would be 6x. Did you follow that? Okay. All right. That's the partial of that with respect to x, and with respect to y is going, oops, I'm off my minus sign, okay, would be also a minus 6y, e to the minus 0.3 times x squared plus y squared. Okay, sorry, I'm running out of room. Okay. And that's an angle bracket following that. Whew. All right. At t is equal to 0.6 seconds, let's plug that in here. And that would be your x at 0.6 is okay, it's minus 6 times your sine of 1.2 okay. I probably don't need the parentheses, they may just screw us up. Okay, I need all the room I can get. Okay, e to the minus 0.3, and then x squared, which is sine squared, no, x squared is your cosine. I just plugged in sine. Yeah, we're out of time. Yuck. They rounded like crazy, and I guess that's what you have to do here. No, they didn't. Not yet. We'll have to pick that up and go with it next time. We'll pick up on example 4, and hopefully we won't redo a lot that we've already done, but we'll pick up and go from there next time. Boy, I didn't get a lot accomplished today, I don't feel like. But anyway, well, we did too. Homework exercises here. Any of the odds, either 1 or 3 or both, either 5 or 7 or both, any of the odds 9 through 19, and we'll stop there. We'll pick up with directional derivatives next time. I hope you feel better. And I hope are you going to be here for the next class? Wait, you are? Okay. All right. Wait. No, you're not in. No, you're not in Cal 3. I mean, you're not in differential equation. You're in physics. You're coming back for physics. Is that right?
Okay. I got a question.
Yeah.
So this is finding the limit.
Right.
Okay. So this is all t. It basically takes equal 0, right?
Okay. All right. Parameterize the curve. Let me go and turn this off. Not that I'm